Hi, Dave. Can you hear me?
Hi, yes, I can.
All right. So far, you're the only participant.
But it's funny, I was just thinking, I was remembering a day on a special victims unit set where the lead actor would keep talking to me for 10 minutes after they called action. He was bored out of his mind, 10 seconds. I mean, he knew when they were actually going to use footage, and that's when he went into character. So like people are getting better and better at arriving on the spot, or, maybe they're blowing it and getting late, whatever. I mean,
Oh, well.
Yeah.
Yeah, well, we've done all the hard work, so I hope.
Well, it's, surveying is great. So, people shouldn't miss it. You never know. Some people may be planning to use the, for some reason, I'm not seeing your other screens.
You're not seeing me?
Oh, there I are. Yes, now I see it. I just had maybe Zoom got updated. Oh, there we go.
Mm-hmm. So I got a message from Gordon who said she couldn't make it today. She had to miss last time too, but she was looking forward to
the recording,
looking over the lecture tonight.
Yeah.
Mm-hmm.
Well, your notes must be a lot of work.
Hi, Alex. How are you?
Oh, hi.
You're hanging in there, huh?
Yeah. I wasn't really able to follow the last two lectures, well, mostly due to bad internet, but maybe I'll just go back in the recordings and it'll be nice though.
Well, I think today you'll see what the point of those lectures was. Because today they're not going to be any formulas. It's just going to be a bunch of pictures.
Good.
Yeah, I agree. The material I covered over the last 3 or 4 lectures was the most technical of everything we're doing. But it's the key technical ingredient. All right, well, I'll start. So we're finally in a position where we can take our family of Morse functions, have a good path of functions. So this is a path in the open stratum of excellent Morse functions union the codimension 1 strata, which has 2 components, if you remember. It has the birth-death components, depending on which way you cross, and it has the crossing components. And we saw early on that the excellent Morse functions, so the Morse functions whose critical points have distinct critical values, that's an open dense set. That's a codimension 0 stratum. And codimension 1, if you have a path, you can deform it slightly so that it lies in the union of the excellent Morse functions, the functions with a single birth singularity, and the functions which are Morse, but where 2 critical points agree, the sort of crossing components. Okay, so we have a good path, and by good path, I simply mean, so if this is a codimension 1 component, the path comes in, hits that component, and then crosses over. Okay, so there'll be a finite number of birth or death points and a finite number of points where 2 critical values cross, and otherwise you have an excellent Morse function. And the endpoints F0 and F1 are supposed to be excellent Morse functions. They don't lie in the critical set. Okay. So we've associated to such a path a graphic. There's the value of the critical point, and there's the parameter value, and this graphic is contained in the interior of the square. It has bursts, it has deaths, it has crossing points, and so on. And it's some graphic like that. And our goal now is to start simplifying this graphic. And what I'm going to talk about today is I'm going to arrange it so that the critical points are always ordered by the index. So as you move up the t value, the critical point, the index is a weakly monotone increasing function. Okay. So before I do that, let me just remark something that I never said before. Suppose you have a path that has no action in it whatsoever. So the critical values just move along, never cross each other. There are no bursts or deaths. So if f lambda is a path in f naught of v, so these are all excellent Morse functions, but the critical values can move and so on. First thing is you can follow every critical point. So you can identify the critical points of f lambda with those of f in a continuous way, and likewise you can identify the critical values. They'll move continuously with lambda. But in fact, because the action of the diffeomorphism group, so the orientation preserving diffeomorphism group of W cross the interval, you act by the diffeomorphism of W on one side, then you apply the function, you apply the diffeomorphism of the interval on the other side. That has local sections in f naught of v. So this group of diffeomorphisms acts preserving this open subset f naught of v, and given any point in f naught of v, there's a small open set that can be lifted back to the diffeomorphisms. So if you have some f in f naught, you can find an open set u and a function g from u into the diffeomorphisms. Say g of the point f is the identity, and g of u acting on f is f sub u. In other words, you have this open set in f naught. You have this base point for it, little f. You can find a section up in the diffeomorphism group, so that if you act by this section on f, you get the original open set u. And that means you can apply these diffeomorphisms to straighten out this topologically trivial path where there's no action in the graphic. You can straighten it out, so in fact it's constant. So nothing changes. So applying a one parameter family of diffeos, we can make the path f lambda a constant path. Of course, not fixing the endpoints. You have to let the endpoints move. So that's an indication that the graphic contains a fair amount of information. Okay. Now, in order to simplify the graphic, I have to use the codimension 2 strata. If I don't use the codimension 2 strata, I can only move the graphic around by a diffeomorphism in the square. Can't do anything else. I can't affect any any other action to the graphic. But if I use the codimension 2 strata, I can change the graphic. And I want to go through the codimension 2 strata and their effects on the graphic. So the first is the intersection of two codimension 1 strata. So this would be two crossing components, or a crossing component with a birth death, or two birth death components. Okay. And all of these, it's easy to see the strata actually cross transversely. So this is a nice picture of a slice to the codimension 2 stratum. So what is a point where the crossing strata meet? Well, that's a parameter value lambda where you have two crossing points. Okay. And what's the effect of going around the boundary of this codimension 2 stratum? Say, starting here, let's compare the path that goes over the upper hemisphere with the path that goes around the lower hemisphere. Okay. To go over the upper hemisphere, I first cross one, I use one of the two crossings, and then I follow it by the other. So going this way gives a path where one of the crossings appears first, and then at a later lambda value, the second crossing appears. Whereas if I go the other way, I simply reverse. I do what was the second crossing first and the first crossing second. So in other words, if I have a graphic like this with two independent crossings in it, one slightly before the other, so the graphic looks like this, I can change it by simply sweeping the path across this codimension 2 stratum until this comes first. And then we have the second one. Okay, so I can interchange the order of these two crossings as long as they're really independent. And that independence is reflected in the fact that I'm at an intersection of these two crossings. It's exactly the same thing for all the other possibilities. If you have a crossing and later a death, as long as they're, again, independent, you can replace that by doing the death first and then the crossing. Okay, same for a birth and same for two deaths, two births. That's one other thing I want to say. If you have a death and a birth like this, with no critical levels in between, you want to interchange the order of the birth and the death. Well, that means the birth is going to come before the death. And in fact, you can do it in either way. You can put the birth below the death, or you can put the birth above the death. Excuse me just a second. It seems we have groceries. I have to take a 1-minute pause. Sorry about that. Gotta eat. All right, where was I? Yeah, so you can, as long as you have independent singularities, crossings, births, or deaths, you can, and they occur one right after the other in the graphic, you can interchange the pictures. Okay, so that's what the intersection of two codimension 1 strata give. Now there are two codimension 2 strata that I have to, actual really codimension 2 strata that I have to think about. And they are what are called beaks. A beak, and then a swallowtail, which I'm not going to use today, so I won't say much about it, but let me just remind you what they are. A beak is when you have the codimension 2 stratum where you have a birth or a death, and you have another critical point at the same level. So we have a critical value with a birth and a Morse, non-degenerate Morse critical point in the pre-image. So of course, even though these lines in the graphic collide here, the cusp point meets the smooth line of the non-degenerate critical point, in the manifold, these in the level set, these singular points are disjoint. You have the Morse singularity in one part of the manifold, and then over here you have a birth. Okay, and the swallowtail is the singularity minus x squared plus norm y squared plus t to the fourth, and nearby, I've talked about this before, but there's a 2-parameter family nearby, t to the fourth minus, oh, I forget, eta t squared plus c t is what you add. That's the eta and c, or the 2-parameter family. And what you find when you go around the swallowtail, well, there's 2 regions. In here, there are 3 critical points, and out here there's 1 critical point. These are birth singularities. This is the codimension 2 singularity here. If you go from here to here, you see a graphic like this. And if you go the other direction around here, you just see 1 single critical point. 1 single critical point. So a swallowtail allows you to take a configuration like this and replace it with a single non-degenerate Morse singularity that goes from, connects up to here and here. So as I say, I'm not going to use that today, so I'm not going to talk about it anymore right now. Okay, now, sorry, there's one other, there's a triple point. So there's a beak, a swallowtail, and a triple point. A triple point is codimension 2 singularities where you have 3 lines crossing. And it's not too hard to see. What you've got here is 3 critical points, all at the same height. So all with disjoint ascending and descending manifolds. And the codimension 2 is simply the relative heights of the critical points, which you can move freely. So in fact, what a triple point allows you to do is if you see a configuration like this, it allows you to move it to that. As you move across this codimension 2 stratum, you replace this kind of graphic with that kind of graphic. Okay. So we have the beaks that allow us to move. Well, I should have said you can move. What a beak allows you to do is move a critical configuration like this to one that crosses both of the arms of the beak. Okay. So those are the local movements we can do by crossing codimension 2 strata. And now I'm going to apply this to order the critical points. I'll tell you what that means, and then I'll go through the argument using these moves and our theorems about descending paths that we proved last time. Paths and bursting. All right, so suppose you have a Morse function. So suppose you have an excellent Morse function, one whose critical values are distinct. And we define the inversion number of F is the number of pairs C1, C2 of critical points with index of C1 minus index of C2 times F of, let's see if I get this right, F of C2 minus F of C1 positive. Let me see if I've got that right. So this says for this number to be positive, why? By revert, what I want to say. Let me do it the other way. C1 and C2, and then I think I need it to be negative. So if this number is negative, if I reverse the roles of C1 and C2, I'll change both of these factors by the same sign, so I won't change whether or not this is positive or negative. So I might as well assume the index of C1 is greater than the index of C2. And this says that C1 occurs below C2. So an inversion is where C1 is below C2, but the index of C1 is greater than the index of C2. So that's an inversion. So we're hoping to order the critical points so that when the critical values, so that when we come up from the bottom, as we go up, the indices of the critical points never decrease. So this would be an example where you move up and the index decreases. Now, these don't have to be next to each other. We might have lots of critical points in between with various indices that we say nothing about. But we look at all possible pairs of critical points where this one has lower value, the critical value than this one, but bigger index. Okay. And the number of such pairs, unordered pairs, is the inversion number. Okay. More generally, if F is a general element, well, okay, so now let me back up a second. I want to define f sub nu of these excellent Morse functions. So these are Morse functions f such that the inversion number of f is less than or equal to nu. So we have increasing sets of the space of excellent Morse functions, allowing more and more inversions. So f naught of v would be what we'll call ordered Morse function, excellent Morse functions. In that if C1, if f of C1 is less than f of C2, then the index of C1 is less than or equal to the index of C2. So as you move up the values, the index is a weakly increasing function. Those would be the ordered ones, and that's where we're trying to end up. Well, this is all a discussion of excellent Morse functions. If I have a more general element of V, I'll say that f is in f tilde of V, some extension, if all f prime in some neighborhood of f intersect excellent Morse functions are in f tilde v naught. Okay, so for excellent Morse functions, you just look at the number of inversions. For a more general function, you look at all possible approximations by excellent Morse functions, and among all the approximations, you take the maximal number of inversions, and then that's the function is said to be in f naught tilde v. In fact, I don't need this great generality. I'm only going to consider what I'm going to call f naught. Well, we have f naught tilde of v, which is just f naught of v. And then we'll have f1 tilde of v, and I'll say what that is. So if you have a crossing point, C1 and C2, you have an inversion number on this side and an inversion number on that side, and you take the larger of the two. Now, they may be the same. If C1 and C2 have the same index, then the inversion number on this side is the same as the inversion number after the crossing. If C1 has a bigger index than C2, the inversion number goes down by 1 when you make this crossing. And if C1 has if it's got a smaller index than C2, the inversion number goes down by 1 when you make the crossing. If it has a bigger index than C2, these are correctly ordered here and incorrectly ordered over on the other side, so the inversion number would increase by 1. So if you do a crossing, you can have the same inversion number on the two sides, or on one side, you'll have one bigger inversion number than on the other, and this would be the larger of those two. If you have a birth, more interesting things happen. C1 and C2, the birth it can't decrease the number of inversions. Obviously, all the inversions you had before, you still have afterwards. These two are ordered, so they don't add to the inversions, but you could have indices less than the index of C1 above C1 and indices greater than C2 below C2. So this could add quite a bit, could add an arbitrarily large number as you cross this birth, but it doesn't decrease the number. And if you have a death, just the opposite happens. The death will either leave the number the same or decrease it. So how can a birth or death leave the number the same if all the critical levels below C1 contain points with index less than or equal to C1, and all the critical levels above C2 have indices greater than or equal to C2, then this birth does not affect the inversion number. Otherwise, it does by at least one. So the only way a birth or death cannot affect the inversion number is that all the indices less than or, let this be index I and I plus 1, then these are all the indices less than or equal to I, and these are all the indices greater than or equal to I plus 1. Then it won't affect the inversion number, which would be the sum of the inversions up here and the inversions down there. Okay, so we have this increasing sequence. I'm only going to be interested in well, F naught. Sorry. So I have this increasing sequence. Okay, so these are the ordered ones, ordered paths. These are the paths with at most one inversion anywhere in the path, and so on. And we just keep going. Okay. And what I'm going to show is theorem for any nu greater than or equal to 1, any path in f tilde 1 of nu plus 1 with endpoints in f tilde nu 1 is homotopic. Any good path is homotopic through good paths relative to the endpoints to a path in f tilde 1 nu. So if we think of ordering these things now, so this is f tilde nu and below here, and this is f tilde nu plus 1. Any path like this deforms relative to its endpoints to a path purely in f nu. Well, so as a consequence, if gamma t is a path with f naught equals gamma naught and f1 equals gamma of 1 in f naught naught, in other words, ordered excellent Morse functions, then gamma deforms, it's a good path, of course, deforms rel the endpoints into f tilde 1 naught. So it deforms into a path so that all the critical values are ordered by index. So that's the ordering we want. So the path, so that would imply that anytime you have a crossing in the path, C1 and C2 have the same index. Because otherwise, on one side or the other, the path would be unordered. And anytime you have a birth or death singularity, and this is index I and I plus 1. Below here are indices less than or equal to I, and above here are greater than or equal to I plus 1. So these bursts and deaths appear in the region between all the critical points of index I below and all the critical points of index I plus 1 and above. And everything is ordered for the good Morse functions. So that's our first theorem, that we can order the critical points in this sense throughout the path. And of course, the proof of the corollary from this relative result is, so proof that the theorem I stated implies the corollary. Well, you have F0 and F1 excellent Morse functions that are ordered, connected by a good path, gamma of lambda, let's say. Just by compactness, gamma is contained in F tilde 1 of nu plus 1 for some nu plus 1, just compactness. So by the theorem, gamma is homotopic to a gamma 1, a gamma prime, rel endpoints in F tilde 1 nu, another good path. So go by induction until gamma is homotopic to a gamma prime in F tilde 1 0, which is exactly the statement. Okay, so this is the fundamental result that's going to allow us to order the critical points. We need to study these paths with endpoints with at most nu inversions. The endpoints have at most nu inversions. The path has at most nu plus 1 inversions. And we want to deform that Rayleigh endpoint so that the number of inversions is at most nu. Okay. Standard sort of inductive argument. Okay. Well, so let's find generators for this relative group. Well, it's not a group, it's a relative set. Sorry, 1 of nu. Okay. So the picture I'm going to draw is my choices. Let's do blue. This blue line will separate F tilde 1 nu from F tilde 1 of nu plus 1. So it includes all of this stuff. This is F tilde nu. Okay. And now I have a path like this. Now this path can cross lots of different codimension 1 strata. But in particular, it has to cross a codimension 1 stratum here and a codimension 1 stratum here. Okay. Now, a crossing crossings come in, well, crossing F1 alpha or F1 beta come in 3 types. They are those that increase the inversion number, those that decrease the inversion number, and those that leave the inversion number invariant. We'll call them increasing, decreasing, and neutral. Okay. So this guy has to be an increase because you're going from F nu to F nu plus 1. The only way you can do that is increase the crossing number. And this guy has to be a decrease. And the amazing fact that from this setup is all of these have to be neutral. They cannot affect the crossing number. Because if they lowered the crossing number, I would be back in F nu. If they raised the crossing number, I would be in F nu plus 1. So they can neither raise nor lower the crossing number, the inversion number. So you start with lower inversion number less than or equal to nu. You make a cross here and it jumps up to exactly nu plus 1. Then it stays at nu plus 1 through all of these traverses. And then when you get back over here, it decreases back to nu, less than or equal to nu. Okay. So on the other hand, for each of these regions, for each of the regions, each of these intervals here, I don't want to say it, for each interval in the path gamma intersected with nu plus 1. So each of these regions here, this one, this one, this one, this one, this one, each of these regions lies in a component of F naught with inversions, clearly, because it has nu plus 1 inversions and nu is greater than or equal to 0. Okay, that implies there exist, for each of these regions, there exist 2 successive, one after the other vertically, critical points, C1 and C2, nothing in between, no critical points in between, with the index of C2 less than the index of C1. That's an inversion. You see, if you have anywhere an inversion, you have to find an inversion of 2 successive members. That's sort of obvious. I won't go through it. Okay, but if C2 is, if the index of C2 is less than C1, that implies there exists an elementary path, or path, an elementary descending path moving F of C2 below F of C1 and affecting nothing else. This is our lemma that elementary descending paths, or in fact all paths, are homotopy equivalent to the space of descending disks. But under these index conditions, general position tells you that there is a descending disk of C1 that misses the ascending disk for C2 and therefore descends below the critical level for C2, that being since there are no other critical levels in between. And once I have a descending disk from C2 passing below C1, I can construct a descending path. Okay, so for each of these regions, there is a descending path. Okay, what does that descending path do? It changes the crossing number, it reduces it by 1. But the inversion number, but the inversion number up here was always nu. So if I reverse the inversion number by 1, I get back into F nu. So for each of these regions, I can find a descending path starting at, say, the midpoint of the region and moving back down, doing one crossing, and that crossing moves me back into nu. Okay. So what I see is now 3 types of, well, now I see now I see some generators. So generators for the relative fundamental group. See, the point is, of course, that this path is homotopic to the composition go up, come back down, then go up, around and down, up, around and down, and so on. So my paths look like this. So again, we have this crossing from F nu tilde 1 to F tilde nu plus 1. Okay. So we have a plus crossing, and that's when we cross here. This could be a crossing or a birth. And then I come back down by a crossing. This can be either a crossing or a birth. Can't be a death because deaths don't increase the critical points. So that's the kind of generator you see out here at the edge, at the extremum. The other kind I can have is a crossing. So a crossing that increases, then some sort of either crossing or birth up here, or death. But a neutral one. It doesn't change the inversion number, and then a crossing back that lowers the inversion number by 1. And then at the very last, I have the inverse of this guy. So a crossing here and a birth. Well, it'd be a death in this case, death or crossing. Okay. Well, this path is the inverse of that one. So if I can show these paths, what I'm going to do is show every one of these paths as homotopic rel endpoints to a path in F nu. So if I can show it for this one, I get it by reflecting the path for this one. So I only have to consider these kind of generators. So a crossing or a birth, and then followed by another crossing. This one raises the index to nu plus 1. This one lowers the index by 1 back to nu. And the other, a crossing, either a neutral crossing, a neutral birth, or a neutral death, followed by another crossing. Once again, I can interchange birth and death by just flipping over this path. So I'll only consider crossings and bursts. Okay, so those are the elementary paths I have to consider. So what about crossing? So let's consider crossing, which increases the inversion number from nu to nu plus 1, and a crossing here that reduces the inversion number from nu to nu, from nu plus 1 back to nu. Okay. Well, there are three possibilities. The crossings can be independent, disjoint, let's call them. So that would be a diagram like this. Here's your first crossing. This is a plus crossing. And then either above or below it, you have a minus crossing. But the four critical points involved are disjoint. That's what I mean by disjoint crossings. So you start with something here that has inversion number nu. You make a plus crossing, and here you have inversion number nu plus 1, and then you make a minus crossing, and over here you're back to nu. Well, I just use my interchange limit. If these are really disjoint, these are independent crossings, and I can interchange the order and make it look like do the second crossing first. Okay, so now this is still a minus crossing, and this is a plus crossing. So I start with something of inversion number nu, it goes down to inversion number nu minus 1, and it comes back up to inversion number nu. Well, that's in f tilde nu 1. So just interchanging these two brings the path, is the homotopy of the path down here. So that's completely trivial. Another possibility is it's the same two indices. I like these pictures, these fun pictures. So that would be, you have a crossing of C1 and C2, which increases the number, the inversion number, and then the same 2 points cross again, C1 and C2. Well, so what you have is, here's the line between F1 and F2. It's also where these crossings occur. We go up to some F and we come down. So we have F0 and F1. But this is the homotopy. So F is in here somewhere. So what I have is a homotopy from F going the two different directions, which in both cases, as I move out from F, the crossing number is now negative. So the index of C1 is less than the index of C2, and I'm moving it past. So my lemma, it says that in that case, the descending disks are in fact homotopic, and therefore these paths are homotopic through good paths. And the end of the homotopy, you see, is the homotopy you need in F nu between F0 and F1. So in other words, basically you can just push C1 up above F by the uniqueness of these descending paths when the index of C1 is less than the index of C2. Okay. So the last case, and the most interesting case, is when there are three indices involved. Sorry about that. So I have a crossing, C1 crosses C2, and this is a plus crossing, meaning the index of C1 is greater than the index of C2. Now, the third critical point could either be above or below. It's completely symmetric picture, so I might as well assume it's below. It's C3, which now crosses C1. This is C2, okay? And this is a negative crossing. So what does this tell us about the indices? This tells us that the index of C1 is strictly less than the index of C2. That's why this increases the inversion number. And this tells us that the index of C3, sorry, I did something wrong here. So the index of C3 is also greater than the index of C1. No, is that right? This reduces the number of inversions. Yeah, so the index of C3 is bigger than the index of C1. That didn't work. I've done something wrong here. The index of C1 is less than the index of C2 because this inversion, this increases the inversion number. It means it takes something that, no, that's right. Let me just think about this for a second. So this increases the inversion number. So I had something that was bigger beforehand. C1 was bigger and moved it below. So we have that. Good. So that gives me the right thing. So the indices of the critical points are C3 is less than C2, is less than C1, is less than C2. They're ordered that way. In particular, the index of C3, it's greater. The index of C3 is greater than the index of C2. That means there exists a descending path from C2 that crosses C3. Okay, so I'm going to extend this diagram. And this is a minus crossing. Okay. So already we were in F nu here. So we started and ended in F nu. And I have a minus crossing here. So this whole part of the diagram is contained in F nu. Okay. And I should have made this maybe red, so as not to confuse it with the diagram. Okay, but look, we have a triangle in this diagram now. Well, so this is all in F nu, so in the end, it's irrelevant for me. And I have a triangle now. The triangle has C1, C1, I don't want to do the triangle. I guess I can do it this way, C1, C2, and now C3, well, it's over here, C3. Well, my triangle lemma tells me I can move to a triangle over on the other side. So I can move this diagram to one that looks like this, where C3 crosses both of them and then stays above. So I traded a triangle over here for a triangle here. And now this is a minus crossing, and this is a minus crossing, and this is a plus crossing. So I start at inversion number nu, I go down to nu minus 1, nu minus 2, up to nu minus 1, and I end up here at the end of this path. And so then I could just add on the end of this path, which adds one more crossing to get back to the original endpoint. But anyway, this is a path in F nu, so it doesn't matter. So you need the triangle inequality in this case to reduce to deform the path into nu minus. Okay, so what have I done? I've done crossing. How much time have I got? Got 15 minutes to do the rest. Now let's talk about birth crossing. So now I'm going to have a birth, which increases the inversion number. And now I'm going to have a crossing that decreases the inversion number. Okay, so here's our birth. And then again, there are going to be some cases. Suppose the crossing and the birth are disjoint. So that would be a picture like this. And all you do is use the fact that these are independent and you move this guy forward to get a picture where the crossing appears before the birth. Okay, and then you reduce the number before you increase it. And therefore you've deformed the path down into nu. Now, it's not possible that the crossing involves these two branches. So that's not possible. Simply because the descending disk for this critical point has homological intersection with the ascending disk for this critical point, non-trivial homological intersection. So there can never be descending disk for this critical point that's disjoint from the ascending disk for that one. So you never do, that's a diagram you can't have. We've done the case when the crossings are disjoint. So the remaining case is when one of the branches coming out of the legs coming out of the birth gets crossed with another critical point. So C1, C2, and C3. And this has to be a minus because this is a plus. All right, well, it's going to be a similar argument. What I do is I use the beak move to replace this crossing by one that goes up and crosses C1. So I replace it by this. So this is C1, this is C2, this is C3. And there are two possibilities to think about on what happens to the indices. So the fact that this is a crossing that reduces the inversion number tells me the index of C3 is greater than the index of C2. The index of C1 is one bigger than the index of C2. So there are two possibilities to think about. Index of C2 equals index of C1, or index of C3 is greater than index of C1. Those are the two possibilities. It's bigger than C2, so it's either one bigger, in which case it's equal to C1, or it's more than one bigger, in which case it's bigger than C2. In this case, moving C3 from below the critical point to above the critical point above the cusp changes the inversion number by -1. It subtracts 1 from the inversion number, because before, when I got over here, I had C3 below C2. Now C3 is above C2, but C3, get myself confused here. Right, C3 was bigger than C2. So when it was below, it causes an inversion, but when it's above, it makes no inversion with C2. And since it's equal to C3, you haven't changed the inversion number with C3. Okay, so moving C3 above the cusp changes the inversion number by -1, and the interchange of C3 and C1 is neutral because they have the same index. So what's happened is the index here is now new. It's reduced by 1. So this is index new, this was index new, and this is index new. So you've deformed the path into F new. In this case, moving C3 above the cusp reduces the inversion number by 2, because C3 is now bigger than both C1 and C2. So if you move it from below to above, you've changed 2 and you've canceled 2 inversions. And the crossing of C3 crossing C1 adds C1 adds 1 to the inversion number. Well, this also then tells me I'm in F new. So this deformation always brings the path, this beak deformation always brings the path into F new. Okay, so those are the paths that come from the end where we have a crossing and we immediately come back down. Now we need to think about the paths that have a crossing, a neutral, cross of a codimension 1 stratum, and then a crossing. So this is a plus, and this is a minus crossing. And this neutral can be, well, I only have to consider a crossing or a birth, the other being symmetric. Okay. Well, let's do the case of a birth first. So I have a crossing, then I have a birth, and then I have another crossing. So suppose they're all disjoint. Start with that picture. Well, then you can move them arbitrarily. So this is a crossing that adds 1. This is a birth that doesn't do anything. And this is a crossing that subtracts 1. So simply move this guy to the front. And then you lower the inversion number by 1, you raise it by 1, and you don't do anything. So that's the deformation, gives the deformation to F. Okay. In fact, next, let me consider the case when the crossings can intersect, have an overlap, but the birth is disjoint. So now the birth is disjoint. But the crossings can either be, well, you can imagine crossings like we talked about before, and then somewhere else, the birth. Well, once again, I can move the birth to the front. That doesn't change the inversion number. So moving the birth to the front so that it's first, and now you do these crossings, this doesn't change. So the inversion number after you pass the birth is still new, unchanged. And now we're back to the pair of crossings. So this is a pair of crossings. And we've already studied that case. Crossing that goes up, crossing that comes right back down. There are 3 cases. This is one of them. Okay. So that tells me that the only cases that are left to consider is when the birth is somehow intersects the crossings, interacts with the crossings. Well, it can't interact with the first crossing because the first crossing happens before the birth. So the only thing that can happen is that the birth must interact with one of the branches coming out of the first crossing. And again, there are 2 pictures depending on the relative positions of these. All right, so this would be our picture here. We have our birth. We have a crossing of C1 and C2. This is C2, C3, C4. And our indices, the index of C1 is greater than the index of C2 because this adds, and the index of C2 is greater than the index of C3. So this is going to look familiar. Right, and this is C1. And therefore the index of C3 is greater than the index of C1, which means that I can add a descending path for C3 to cross C1. And this is a negative intersection, so it stays in F nu. And once again, you see, that didn't work. Maybe I didn't do the right thing. Maybe this is not the right argument. Let's see what I said before. Yeah, I think it's more, I don't think I did that right. Let me back up here. Let's just go back here. I think what I want to do, rather than what I was just talking about, is use the beak move again. Let me go back to the picture. Right, so that's the picture. So we can do a beak move. We can move C2 across the cusp, and we get a picture like this. Sorry, C3 and C4. Okay. C1, C2, C2. Okay. Now, so what we know is that the index of C2 is greater than the index of C3 because this is a move that decreases the inversions. And we have the same 2 cases we had before. If the index of C2 is bigger than C4, doing this beak move changes by don't know how to do this one. Well, that's a good time to quit. So I have one last diagram that I owe you. It follows the same pattern as before, but for some reason I can't quite see it. But what I'll do next time, okay, I'll finish up this diagram next time, or maybe I'll just write it up. And then we'll work on using the swallowtail and Smale's cancellation, now that we have the critical points ordered, to start eating away from the ends, kill the lowest critical points, kill the highest critical points. We choose some intermediate level, and we're going to kill down until we have only critical points of index I and I plus 1 for any I away from the two extremes. And then we'll be set up for the algebraic K theory to show how we kill off those last two regions. So I am writing up the notes from last week. I hope to have them out later today, and I'll write this up, draw some pictures also in the next day or two. All right, so that's where we are. Thank you, those of you who stuck in there.
Yeah.
And I'll see you on Wednesday.
Great.
So